In lesson 5.6, we're going to talk about the second law in trigonometry, the law of cosines. We're going to use this law, just like the law of sines, to help solve right triangles. So the law of cosines says, in any triangle with angles A, B, and C, opposite of sides A, B, and C respectively, the following equations are true. So now we can set up, it's a form of the Pythagorean theorem. C squared is equal to A squared plus B squared minus 2AB times cosine C. Okay, so the thing to be familiar with this formula is whatever side length we have isolated by itself, that is going to be the value we take the cosine of the angle for. Okay, just like if we look at the bottom one, if we have A squared isolated by itself, we're going to be taking the cosine of A later on in the equation. Example 1, we want to solve triangle ABC. In this triangle we're given, we know one of the angles, angle C, is 20 degrees. We know two of the side lengths. Little b is 5, little a is 11. We do not know what C is. So we can use the law of cosines to first find that value of C. Then we can use either the law of cosines or the law of sines to find those missing angles. Okay. So if we're looking for that C value, we have C squared equal to A squared plus B squared minus 2AB cosine of C. So now we can plug in everything we know. C squared is equal to, our A value is 11, plus our B value is 5, so we're going to square each of those, minus 2 times 11 times 5 times the cosine of C, which is 20 degrees. So if we type this in on a calculator and simplify, okay, type all that in on the right side, we get 42.63. C squared is equal to 42.63. Then to get C by itself, we'll have to take the square root of each side. So C is approximately square root of second answer. And we get 6.53. So now we know all three side lengths. We could use either the law of cosines or the law of sines to find these missing angles. For this problem, we're going to use the law of cosines to find those angle values, because if you use the law of sines, there's actually a little trick you have to use involving supplementary angles to find the exact angle. So if we take our law of cosines and isolate cosine of A by itself, we could rewrite that formula to get A squared minus B squared minus C squared, all divided by negative 2BC. So now if we plug in the known values we have for A, B, and C into a calculator, you type that in, simplify, you get this nice looking number. So if we have the cosine of A is equal to this value, negative 0.817. If we want to get A by itself, solve for that angle, we have to take the inverse cosine function. So if I go second cosine, we have the inverse, and we're going to take second. If I push the answer key, we get a value of 144.8. So the measure of angle A would be equal to approximately 144.8 degrees. Okay, so now we know what angle C is, we know what angle A is. To find the measure of angle B, we would have to take 180 and subtract those other two angles to get approximately 15.2 degrees. Okay, so in this problem we use the law of cosines to solve for the missing two angles and the missing side length. Example 2, we're going to solve a triangle that has all three side lengths, but we do not know any of the angles. So we're going to use the law of cosines twice to find two of the angles. Once we have two of them, we can simply subtract them from 180 to find the third angle. So if we try to find angle A, if we rearrange the law of cosines, we'll get the cosine of A equal to 9 squared minus 7 squared minus 5 squared, all divided by negative 2 times 7 times 5. So if we type that in on our calculators, we get approximately negative 0.1. And then if we want to solve for that angle, we have to take the inverse cosine of each side. So if we take the inverse cosine of that value, we get approximately 95.74. So the measure of angle A would be approximately 95.74 degrees. So using a similar idea, if we want to solve for the cosine of B, if we get the cosine of B by itself, we'd have 7 squared minus 9 squared minus 5 squared, all divided by negative 2 times 9 times 5. So now if we would type that in on our calculators, we would get approximately 0.63. So if we want to solve for that angle B, we have to take the inverse cosine of each side. If we take the inverse cosine of that value, we get approximately 50.7 degrees. So the measure of angle B would be approximately 50.7 degrees. So now the final step, we found two of the angles. So if we want to find the third angle, we simply take those two, subtract them from 180. So the measure of angle C would be approximately 33.56 degrees. Okay. So now we started with all three side lengths. We could use the law of cosines to find some of those missing angles. Next thing we're going to talk about is the area of a triangle. In geometry, you learned the formula area equals 1/2 base times height. Now in trig, we can use sine to be able to find the area of many triangles. Okay, whether they're right, acute, or obtuse, we can use these formulas to find the area. Okay, so if we're looking for the area, all we need are two of the side lengths and the included angle between them. Okay, so there's three different formulas we could use based on the type of triangle we have. For example, if we had a triangle A, B, and C, A is equal to 7, B is equal to 6, and the measure of angle C is 60 degrees. Okay, so if we plug this into the formula, area equals 1/2 times 7 times 6 times the sine of 60 degrees. So the area of this triangle would be approximately 18.2 square units. Okay, whether we're centimeters or inches, 18.2 units squared. Okay, so one new way we can use to find the area of a triangle. Another way we could find the area of a triangle is called Heron's formula. Okay, this is named after Heron of Alexandria. He was credited with discovering this formula to find the area of a triangle. There's debate on whether he actually discovered it first. Many people think Archimedes of Syracuse, who has a lot to do with mathematics, made many discoveries, actually discovered it many centuries earlier. Okay. Whether who discovered it or not, we're going to use it to find the area of a triangle. The area is equal to the square root of s times s minus a times s minus b times s minus c. A, B, and C represent the side lengths of the triangle, and S represents the semi-perimeter, meaning we add up all three side lengths, that gives us the perimeter. If we divide that by 2, that gives us the semi-perimeter, half of it. Okay, so that's what S stands for, the semi-perimeter. It's half the perimeter of a triangle. So, example 3, we want to find the area of a triangle with sides 13, 15, and 18. Example 3, we want to find the area of a triangle with sides 13, 15, and 18. So the first thing we have to do is find the semi-perimeter of this triangle by adding all three side lengths together. and dividing by 2. So if we add 13 plus 15 plus 18, divide that by 2, we get 23. So now we have all three side lengths, we know the semi-perimeter. Now we can plug these values into Heron's formula to find the area. So the square root of 23 times the quantity 23 minus 13 times the quantity of 23 minus 15 times the quantity of 23 minus 18. We can simplify that down to the square root of 23 times 10 times 8 times 5. And now you can type that in to get an approximation. So the area of a triangle with side lengths of 13, 15, and 18 would be approximately 95.92 units squared. Example 4 is an application problem. The bases on a baseball diamond are 90 feet apart, and the front edge of the pitcher's rubber is 60.5 feet from the back corner of home plate. Find the distance from the center of the front edge of the pitcher's rubber to the far corner of first base. Okay, so some key pieces of information. The distance from home to first is 90 feet. The distance from home to the pitcher's mound is 60.5 feet. And if we think about a baseball field, the infield, it's a square, so we know all the angles are 90 degrees. So the angle formed in the triangle we have would be half of that, which is 45 degrees. The distance we're looking for is from the pitcher's mound to first base. So how far, if the ball's hit directly to the pitcher, how far does he have to throw it to first base? Okay. The key piece of information here is that we do not know this is a right triangle. Okay, if it was a right triangle, we could just use the Pythagorean theorem, but we don't know that that forms a right angle. Even though it might appear to be, it does not. So we have to use the law of cosines to find the value of x. So we can write x squared, which is the side we're looking for, is equal to 90 squared plus 60.5 squared minus 2 times 90 times 60.5, and then we have to multiply by the cosine of 45 degrees. Okay, and now we're just going to simply type all that in on your calculator. So if we type that in, we get approximately 4,059.86. If we would take the square root of that, we get approximately 63.72. So the distance x would be approximately 63.72 feet. So that would represent the distance from the pitcher's mound to first base.